depends on how big is your beta, right? So this has to do with the tick size of 2 compared with the size of beta. Okay? So the solution should look like that. Okay? And here we show you if you solve this problem by dynamic programming, you will get qualitatively, you will get these kind of results, right? But then it will sort of show these things exactly. Okay. So here, your control. So you have, so this is a discrete choice. So you have just these 2 options. So you can eat or wait, right? Okay. And then remember in dynamic programming, you need to look at the state variable, right? So the state variable, so here you only have 3 possible values of the state variable. So 0, 1, and 2. Then we can try to formulate the dynamic programming problem. So the return functions, utility, right? Return functions. So the return function depends on the state and your control. Okay, so if the state is 0, no matter what you do, it must be 0. If the state is 1, if you eat it, you get utility 1, right? So we assume you have linear utility. Linear utility. Okay. Linear utility for simplicity. So if the state is 1, if you choose to eat, 1 unit of utility. If you don't choose to eat, 0 utility. Right? Similarly for fixed size of 2. Okay. So this is the return function. Okay. So for this kind of discrete problem, we can only use the table to list out the function, right? We don't have a formula. Okay, but this is a function. So this shows you explicitly the return function is a function of the state and your control, right? For each pair of state and control, you have a value, one single value for the utility. Okay, return functions. And the transition, okay, transition. The transition equation in this case, again, because it is discrete, right? Everything discrete. State and control, they're all discrete, so that we don't have a nice formula. But we can list out all the possibilities, right? Using a table to list out all the possibilities. So the transition equation, so the current state, current control, and then on the left-hand side will be the future state, right? Okay, future state. So here we use, so the table entry will be the future state, x tilde or xt plus 1. And then this is xt, current state, and current control, okay, yt. So if your current state is 0, current control is to eat, next time you don't have anything, okay? So there will be no more cake. Once you choose eat, then it is 0. If it is 1, if you eat it, 0. If it is size 2, if you eat it, next time no more cake, right? Okay, if you choose to wait, if the current size is 0, even though you wait, is 0. Current size 1, next time becomes 2, right? This is our gain. If it is 2, next time the cake will not become bigger, it is still 2. Okay. So this table shows you how the state evolves over time, and it will depend on the current state and also what you choose. Current state and current control. Okay? And then we can write down the Bellman equation. Okay. So here the Bellman equation in this example. Now, the first line will pretty much what we see before, right? So we use this kind of symbol, Vx and then max over your control, your choice of control. And then the return function depends on state and control. And then this is the continuation value, discounted value of next time, right? And then subject to the transition equation. And here, what we try to show you is that for this particular simple example, we want to show you what a Bellman equation exactly look like. Okay, so this is the purpose of this example. So here, this is what we see before, and then you can substitute these things, transition equation here. So this is the future state. This is actually the future state. And here, we want to write it down something sort of looks like the macro model, the Bellman equation of the macro model, the VE and VW. So here, this is, to put it this way, because this is max over these things for two choices, right? Your y variable can only take two possible values. So therefore, when I write down this equation, I can use this kind of notation. So I can evaluate this at each value of y. When y is when y is weight, I write it this way. Okay, so therefore this is a very simple maximization problem. Just given any two numbers, you pick the larger. Right? You don't need calculus, and it's not possible to use calculus. So just to see which two numbers is bigger, and then the optimal choice will be either the first position or the second position. Right? First position stands for E, second position stands for weight. Okay, so we call these things when you evaluate this right-hand side. Okay, so this thing we call it VE, the value of eating, and then this is the value of weighting, and then this is the operator, A and B. Which one is bigger? Right, the max of A and B. Okay. Now, once you have these things set up, you can write down the Bellman equations. It is actually like this. Okay, so you have this three states value 0, 1, 2. Okay, so therefore you have this. So the Bellman equations, when you kind of write it down explicitly, you end up with this. And the solution, what is meant by a solution? So basically, you want to find out the value functions, and as a byproduct, find out the policy function, the control rule. So here, in this case, because the value function can only take three values, V0, V1, and 2. So you want to find out these three numbers, V0, V1, V2. And you can see here, they appears on both sides, right? And moreover, this is not something you can easily solve because of this max thing here. It's nonlinear. You cannot use algebraic manipulation. Okay? So this max thing is very easy if you know exactly the two numbers, but it's not easy to solve or manipulate if those things are a known variable, like x and y here. Okay. So this operation is not easy to manipulate by algebra. Numerically, it is easy. Max of 1 and 5, then you know it's 5, right? Max of 10 and 20 is 20. But if it is x, y, z, it's not easy. So basically, we'll try to illustrate by numerical method. Okay? Numerical method. So here, you want to find out, so this is known as value function iteration. So this is how we solve dynamic programming problem. And here, we try to play computer, okay? Because if we use MATLAB to solve it, you don't understand it, right? I can write it in fact, I have a computer program to solve it. I can show you the results, but you don't understand what is going on. So here we try to illustrate, we go through a few steps So we sort of playing a computer. So the computer is actually doing this kind of operation. So the value function iteration is that you want to find out V0, V1, V0, V1, V2 to satisfy this set of equation. So you start out with arbitrary choice of three numbers. So the simplest choice, you choose 0, 0, 0. Put them into the right-hand side and then use this to find out the left-hand side and then put it back into the right-hand side and then find the left-hand side and so on. So this iteration. So here, we start out with step 0, initial choice. We choose all three 0, plug them into the right-hand side of the Bellman equation, and then use the right-hand side to solve out a update that we call V1, okay? So here, this is the right-hand side, and then we set all three V's to be 0, 0, 0 here. Now, once you have concrete number, it is very easy, right? 0 is 0, max 1, 0, which one is bigger? Must be 1, right? 1. 2, 0, which one is bigger? 2 is bigger, okay? And then, as a byproduct, the policy function. Policy function means that you solve this maximization problem, what is your choice? So this is 0 and 0, so either one, okay? And then what about this one? This max 1, 0. So the max is in the first position. First position means the first choice of the control, and we set our first choice to be it. So the first choice is it. And then here, 2, 0, which one is the optimal choice? The first choice, right? First choice, because the first one is the bigger one. First choice, so it is it. So it. Okay, so this is the policy function argmax of this, the argument of the maximization problem on the right-hand side of the Bellman equation. Okay, so this is after one iteration, you have this tentative estimate of the policy functions, and then the tentative estimate of the value functions. And then you go for another iteration. So you put this thing to go for another step of the iterations, another round of the iterations, okay? So this is what you find from last time, okay? Which is 1 and 2, right? Okay, so this, V10, right? So let me check. So V10 and V11, V12, right? So we have 0, 1, 2, right? This is what we find in the last iteration, 0, 1, 2, okay? So we have 0 here, put 0 here, and then we put 0 here, right? 0 here, and then 1 plus this, so this is 1, and then we have a 2 here, and then we set our parameter, for this case, parameter 0.75, right? And then so we have the 2 times 0.75 here, and so on, right? And then we go through this, see which one is bigger, 1 and 1.5, so 1.5 is bigger. Now this time, the optimal control is the second, right? Second component, which is weight. And then 2 and 1.5, 2 is the bigger one, and the optimal control is the first choice, is the weight. It, right? So it is here. Okay, so you can see here, we play the computer. Now you can imagine, for the computer, this is a very easy problem. And obviously you can have 1,000 states because you just add more rows. The computer just check it row by row. Every time you just check which number is bigger and the position of the bigger number, whether it is in the first position or in the second position, right? So you can imagine for a computer, this is not a problem, right? So just all you need to do is to write a loop. Just loop it over many, many times, right? So this is exactly how we use the computer to solve the dynamic programming problem. This process is hard for us, but it's just tedious. It's not difficult, right? Not difficult, but for the computer, certainly very straightforward. Okay. So here we show you, if you keep doing that for a few times, you will find that eventually it will stop. Okay. So for example, here we find that after 3 iterations, it just doesn't change anymore. Okay, doesn't change, so it kind of converge after a few iterations. So we find that for this case, for this case, when the discount factor is 0.75, your optimal policy, so as a byproduct, right? So your optimal policy, your optimal control. During this iteration, every time we find we find an update of the value function, and then as a byproduct, we find the optimal policy. And then after the iteration stop, we will have the final optimal policy. So the optimal policy here is indifferent and then weight and need. And this kind of obvious, right? Because we know when the cake size is 0, so it doesn't matter. When the cake size is 2, you will never wait because it will never become bigger. Whereas for cake size of 1, it may or may not worthwhile to wait. And here, when the discount factor is 0.75, okay, then it's worthwhile to wait. And by here, if you discount future heavier, you are very hungry. You don't want to wait, right? 0.25, sort of close to 0. Close to 0 means that future utility doesn't matter to you, right? So you're very hungry, and you can imagine you probably don't want to wait. And here we go through the iterations. Indeed, this is the case. After a few iterations, we find you will want it. Okay. So the purpose of this is not really saying that this is a very hard problem, because we should already know the answer. So the purpose of this example is to demonstrate the computer solution of a dynamic programming problem. Okay? So basically, when you write a computer program, you want to kind of follow this sort of logic. Yeah, so we have a program. We follow this kind of logic. Okay. So this is a MATLAB program, right? So it's a MATLAB program. And of course, again, you don't have to follow me to have this exact mapping. That's my problem, okay? So as long as it works, it will work, but I'm the kind of guy who want to have exact matching and so on, okay? So basically, we try to solve the same problem. This is using computer, okay? So there's a MATLAB program, and then here, so here we just certain, so that's sort of a short tutorial, okay? Short tutorial on MATLAB. I think at the beginning of the semester, you also have a workshop, but here just to remind you, refresh your memory. So this command line, right? Percent means comment, right? So you want to comment your program so that next time you know what is going on, and then you can also copy and paste those lines for your purpose. And then here you want to keep the output. So in MATLAB, you want to have this file. So all the output will be sent to this text file. And then this is called a diary, right? So you want to keep the output file. Okay, and then programming technique, because you want your program to be recyclable and you can try out other things. So you want to keep your parameter in one place so that you can easily change the parameter. So I call this the parameter area. So in this problem, the discount factor, convergence, and so on. Okay. So here you have remember that your value function, right? So your value function, you want to do it numerically. So you need to in this particular example, you want to have the three numbers, right? V0, V1, and V2, right? The three numbers. So you want to have a vector to keep the three numbers. So here, first we define the state space, right? So 1/3 vector. And in MATLAB, you want, so this thing will keep it into a column, okay? So the semicolon means column. So this is 3×1, it's one column. And then here the control is 1 and 2, so 2 control. Now, you can attach a label, right? It and weight, but the software will recognize it as a number. Okay, and then we want to keep the value function as a 3×1 vector. So this initial, so we start out with 1, 0, 0, or 0, 0, whatever. And then we want to keep this Bellman equation. Okay, so the two column. So the first column is the first control, right? So it's the first control. Just like the formula. You see here, because you want to do it like, you want the computer to check where is the max, right? Let's say here you have a 1, you have this, you have 2 here, whether it is the first position or the second position. So basically, I want to keep this into 2 columns and let the computer to check where is the max. Is the max the first column or the second column? So I want to keep this, rather than using comma, I want to keep this first term in the first column, this term in the second column. Okay. See, in algebra, you can use comma, but the computer doesn't know it, right? Okay. So the computer will have to, you have to give the computer these 2 terms and then ask it which one is bigger. So you want to keep it, so systematically I want to keep, so this one is the same, so it doesn't matter, you can write it twice. So you want to keep this first term in the first column, and then the second term in the second column. So the first term is the control number 1, second is the control number 2. So I want to program it that way. So in the program, we kind of do it like this. Okay. And you can so we set up this as a 3×2 matrix and then make it into 2 columns, and then just copy in the formula. And here, because you want to do this as an iteration, right? So you need to use a for loop or a while loop. So here I show you how to do it in a while loop. So the while loop is that as long as this condition is true, it will run. Okay? When this condition is false, it will stop. So first, so I have to check the condition. So first, you don't want this loop to run forever, right? So you want to set a upper bound for the iteration. Okay, just as a safeguard. So I set it, at most I want to iterate 1,000 times. So and then in the loop, I count the number of iterations, how many iterations has been done. So you use this counter, IT, first outside the loop set it to 0, inside update by 1 every time. Okay, and then secondly, I want the program to automatically check how big is the difference between 2 consecutive approximation of the value function. Remember in the algebraic example, we start out with V0, and then we calculate V1, and then we use V1 calculate V2, V3, V4, and so on. And obviously, you want the program to check it for you, see if the difference between two consecutive V are very, very small, then you want to stop. Right? So you set your convergence criteria. How accurate do you want to? What do you mean by convergence, right? So you want to set the criteria. So I set a very small criteria. Set convergence criteria, 1 to the e minus 6, so 10 to the power minus 6, right? So 6-digit accuracy. Okay, and then I will check the difference between two consecutive V. If the difference is bigger than the convergence criteria, then the difference is not small enough. Keep going, right? Okay. So here you calculate these things, and then the maximization in the algebraic example, you'll see that the maximization is every time it is just compare two numbers, right? Every time whether the first number is big one or the second number is big. So in MATLAB, it is this function, the max functions. Okay? So to find out, so this MATLAB max function will find out the max column. Okay, so the max column with for each column, find out the maximum number and the position of the maximum number, each column. Because here I want to find out which row, right? So I need to do the transpose here because of the way I set it up. So this will be the max number. This is the index of the position of the maximum. Okay, so in my case, it is either 1 or 2. Okay, and then I will keep the new value function, right? So to compare with the old one. So here this is the difference between two consecutive iteration of the V, right? So V0 minus V1 absolute value because I have, and then choose the maximum element. And so this is sort of a very simple while loop. Okay, and then you see the result if you run this program. So you see the result in iteration 1. You get this. So I write it out. So the state, and then this is the value, and then this is the last column is the policy. 1 for E, 2 for weight, and in my example, it takes 45 iterations. So this loop will run 45 times, okay, before it meets the convergence criteria. So as you can see here, you can have this kind of number here. Okay, so it's not exact. Yeah. So so this gives you an example. Now we have to stop here. I think it might be a class, but you can take a look at these things. We will use that sort of software.
Oh, I have